This is the last section of Chapter 2. So we're going to talk about carbon and why carbon is so important for life and what these things are that we call functional groups. When we start looking at biological molecules, those are going to have a great deal of importance. So let's get started. First of all, I went too far. We know that carbon is a major component, a key component of all sorts of macromolecules, meaning large molecules. These are ones that we typically find in biology, certainly in our bodies and cells. They're the things that build larger structures. So we have proteins and lipids and carbohydrates and nucleic acids. So those are going to be sort of major themes when we're going to go on to the next chapter. But for now, what we want to do is understand why carbon is so important and why it's unique. One of the things we'll notice is that carbon has this ability to form covalent bonds with up to 4 different atoms. So we're going to see how it serves then as a backbone for lots of larger molecules. Each carbon has those 4 electrons in that valence shell in the outer energy level. So once having filled those through covalent bonding with other atoms of other elements, that allows carbon to be extremely stable. It achieves that octet rule. Now, the most basic carbon structures we're going to look at are things called hydrocarbons. And hydrocarbons are simply that, hydrogen plus carbon. And we're going to think of them very often, we think of them as fossil fuels, because it's within the bonds between these carbons and the hydrogens that there's tremendous energy stored. So we'll see some examples coming up. Now, your book doesn't have this, but I do want you to know this because I think this is really valuable for kind of identifying, identifying what certain compounds are. So when we look at hydrocarbons, there's some naming rules which make it kind of simple, in the sense that if you have an understanding of how many carbons there are within that structure, then you can pretty well name it, provided that you also know whether it has just all single bonds or double bonds, etc. So we'll learn this. So let's take a look first of all at the root names. So when there's only one carbon, it has the prefix meth, M-E-T-H. 2 carbons eth, 3 carbons prop, 4 carbons but, 5 pent, 6 hex, 7 hept, 8 oct, and 9 non, and 10 dec. And there's more. I mean, we can go beyond that, but this is kind of just a basic chart to understand. But then when you go over here to the right, and if I can get me out of this equation, which I'm going to try to do right now, what you see when you do that is that we can look now at these hydrocarbons now with their bonding to hydrogen. So methane, meth meaning 1 carbon, and then ANE at the ending means that everything that in this molecule has a single bond. No double bonds, no triple bonds, just a single bond. So ANE tells you that automatically. So when you see these words, for example, propane, which you've heard of, we know that prop means 3, so there's 3 carbons, and then all the rest of the bonds are filled by hydrogen. And that's we can look at its molecular formula, which is that C3H, that's H8, sorry, I wanted to be sure that was correct, where the number of carbons, in this case 3, times 2 plus 2 is going to be the number of hydrogens. So 6 plus 2 is 8. So carbon C3, H8. And that pattern follows all the way down. We can see their condensed formula. That's just a different way to write it, where you're seeing the kind of a little bit more of, revealing a little bit more of the structure. And then this is the actual structural formula, so if we drew it out. And so and these, all of these are called aliphatic hydrocarbons. So they all have single bonds. That's why they have the ANE ending. But they're aliphatic because they're linear. They're just going in carbons in a lineup that just kind of go in a straight line, as opposed to ones that might form some kind of a circular cyclic structure. Now, keeping that same set of naming rules here, so the number of carbons, that prefix doesn't change, that root name, meth, eth, prop, etc. But let's say there's a double bond. So if there's a double bond, so in the case there won't be any double bonds with the first one. You can't have methane with a double bond because it only has a single carbon. So when we're looking at double bonds, we're looking at the bonds between carbons. And you can see that in this picture. So here's two carbons right here, and these two carbons are double bonded. So the fact that there's two carbons means we're going to use that prefix or that root name ETH. But now instead of putting an ANE ending, we're going to put ENE. So ENE indicates that there's a double bond somewhere in the structure. Looking at propane, you can see it here, double bond. So we're going to put the ENE ending. Prop means that we've got three carbons. And also notice what happens when you have that double bond. You reduce the number of hydrogens. So instead of being 2 times the number of carbons plus 2, we just have 2 times the number of carbons for hydrogen. So 2 carbons, 4 hydrogen, 3 carbons, 6 hydrogen, etc. So these are called alkenes, and they're still aliphatic, meaning that they're still a chain of carbons. And when we use the ending, we know that that has a double bond, but it doesn't identify where the double bond is. But in these pictures, you can just see it's like the first one. But it could be somewhere else. So it just has a double bond. It could even have more than one. But we're just going to consider this. Now, why we look at these two in biology, and what your OpenStax textbook is telling you too, is the arrangement of groups around that double bond tell us something about that particular molecule. And if we show the arrangement like this, where the rest of the carbons are on the same side of this double bond, and the hydrogens we can see are sort of the lone wolf hydrogens over here, we call this a cis isomer. Cis meaning it's on the same side. But if we arrange it a little differently, we have these groups across from one another, we call it a trans isomer. Now, this may not be clear to you yet, but we'll get into this again. So this is sort of a preview of this idea of cis and trans. You probably have heard of trans fats, and that is related to this. So we'll talk a little bit more soon. Now, if the carbons instead are not in a lineup like aliphatic hydrocarbons are, but instead form a cyclic structure like this. I don't know what, I think I just X'd that one out because that was one we won't talk about. We put the word cyclo in front of it, and then the rest of the rules hold. So cyclo means it's cyclic, prop means it's 3 carbons, and ANE means that there are no double bonds. So this is a cyclic hydrocarbon. It's the smallest possible one that's out there, cyclopropane. Here's cyclohexane. ANE ending tells me no double bonds. But notice this one down here has an ENE ending, and here you can see between this carbon and this carbon. So each of these points on this structure here represents a carbon. And what would be filling in for the rest, where we would see if this is a carbon here, it's bonded to another carbon here, but we would see the hydrogens also attached. So in this picture, you can't see the hydrogens, but they're there, and we could count them, and we will. So we'll take a look at that soon. Here's methane, just to give you, again, a preview. Simplest hydrocarbon, single carbon. It has this particular tetrahedral geometry, and it has an ANE ending, only single bonds. Again, aliphatic means the chains, so you can kind of see this is really how they look, rather than just drawing the molecular formulas. We can see more structurally how they arrange like this. So tetrahedral. Another one, tetrahedral. Remember, also in this case, both of these have single bonds. And then we get to the one that has a double bond, ethene. You can see the double bond here between carbon-carbon. And what you notice here is that it has a planar structure, a planar geometry. In other words, it's more flat. And the other thing that's true about it is this double bond doesn't allow for any rotation. So these structures have an ability for rotation around the carbon. The carbon-carbon bond can actually twist or rotate and be in a little different orientation. But this is more rigid. So the double bonds cause it to be more rigid. Here's some of those cyclic, or another term for the cyclic is aromatic. So cyclopentane, cyclohexane, this is one that has its own name, benzene. Pyridine, we'll talk about these later. Notice that in this last one, there's a nitrogen in the cyclic structure. So this wouldn't be strictly considered a hydrocarbon, but because it has this addition, but it's still structurally the same. You see all the hydrogens and carbons. So that's a substitution in here. So the next term is isomer, and an isomer is something that has the same chemical formula but can have a different arrangement of the atoms. And so right at the top here, we can see things that are called structural isomers. If you notice that there's 4 carbons, all single bonds, so we call that butane, because 4 is the root word, but is the root word for 4. But this also has 4 carbons, just arranged differently. So these 1, 2, 3 are here, and then another one is down here. This is called isobutane. And I think of it as sort of like this is a little bit isolated from the other carbons. So this is isobutane. Here's that cis and trans idea again. And if you notice on here, it says methyl groups on the same side of the double bond. So methyl groups are this right here. This is called a methyl group. CH3, CH3, CH3. Those are methyl groups. We're going to see those in larger structures too. And then probably the one that's the strangest here is called an enantiomer. And what these are is they are just mirror images of one another. So you can see that the atoms that surround that central carbon, so here's the central carbon, are exactly the same, but one has a left or L orientation and one is called a D isomer. You kind of think of it as right. These are mirror images of each other. So they can't be superimposed. You can't put one on top of the other. It's like your hands, if you think about your hands, in a sense, are enantiomers. If you put them with the palms up or palms down, it doesn't matter. And then you try to put one on top of each other, leaving the palm up or the palm down, you'll see that they don't line up, not that direction. So these are the enantiomers. This is looking at, again, what's the effect of this idea of either of being one of these cis or trans molecules. And I'll talk about this more in class. I don't know why this figure kind of got weird, but we're going to see that it does have a big effect because these long chains of hydrocarbons are found in fats. And some of them are going to, the way in which the molecules are arranged around the double bond are going to cause some differences in the behavior and in the sort of the shape here of these different hydrocarbon chains. And so we can look at things as being saturated versus unsaturated. And we'll talk about this. You can read this when you have your slides in front of you because I think you'll be able to read it better than what you see here. Here's the enantiomers again. And then we're going to get into functional groups. And I'm going to spend more time on just these functional groups here in the next video. So stay tuned. Here it is. We're almost done with this chapter.